All right, guys, today we're going to do our very last video lesson. So you can all do a big cheer when this one's finished, that you don't have to watch any more of these. We're going to carry on with titrations today. So we're going to look some more at those titration curves, and we're also just going to focus a little bit more on calculations. The nice part about the calculations part is you have done titration calculations before, so it's not completely brand new to you. So we'll review how to do titration calculations, and then we'll also talk about something new today, which is called pKa. Okay, so here we go. We'll just talk again about a neutralization reaction. It's when an acid, I used purple today for the very last video lesson. I'm just going crazy here. When an acid reacts with a base to form a water and a salt. Use a thinner line. Okay, so at the equivalence point, which is what we talked about last lesson. Okay, so the equivalence point is when the acid and base have completely reacted and they're neutralized. Okay, so when you're titrating, that equivalence point is right where you'd see the color change occur with your indicator, and that's when you'd stop your titration. So at that point, the moles of the acid would equal the moles of the base, or you could think of it as moles of the hydrogen ion are equal to the moles of the hydroxide ion. Okay, so how do we do the calculations? Well, these are the steps. You work out the moles of the solution that you know, because you always know one solution and the other solution is what you're looking to find out. Then we use the mole ratio to determine the moles of the unknown. And then with that, you can either calculate the concentration or the volume of the unknown depending on the question and what it's asking and what information you've been given. Okay, so here is one example that we can work through. It's a bit of a ugly compound here, but it'll be just fine. So in a titration experiment, 0.5468 grams of KHP. So that's like what we're going to use as the short form of the compound, but the compound's actually potassium hydrogen phthalate, and this is the actual chemical formula. So we'll shorten it up to this, but when we write out our balanced equation, we'll use this. And that's needed to completely neutralize 23.48 milliliters of sodium hydroxide solution. Calculate the concentration of the sodium hydroxide solution. Okay, so we know how many grams we have of the acid. We know how many milliliters or the volume of the base. So what we're first going to do is we're going to write out the neutralization equation. So we've got this KHC8H4O4. Now the way this is written is this H, so this is an acid. Here's your positive ion, and it's actually this KC8H4O4 that makes the negative ion. So just so we can figure out how to write our products, this is what's going to come off, and what's left behind is the negative ion. Okay, so that's going to be added to NaOH. And we're going to now form our products. So our positive ion from the base is going to get together with the negative ion from the acid. So we're going to get this positive ion, and then remember the negative is this KC8. It's everything except the hydrogen, or like this hydrogen, I mean. And then we're going to put together this hydrogen with the OH. So HOH becomes water. So you always get water as one of your products in the neutralization reaction. This is just an ionic compound, which can be called a salt. So everything here, I didn't have to go and change ratios of anything. So this is all, no balancing is required. It's all 1-to-1 ratio. So now what I'm going to do is I'm going to do moles of the known solution. Okay, so I'm going to take moles, and this time I'm just going to shorten it to KHP. So if I know how many grams of KHP I have, I can easily get that into moles. Okay, and how I'm going to do that is I'm going to use the molar mass. So in 1 mole, now this is a bit of a beast to calculate because there's so many to get through, but if you add up the mass of each element in this compound, you would get 204.2. Okay, so grams cancel, and that would work out to 2.678 times 10 to the negative 3 moles. Okay, so we now know how many moles of the acid we have. We want to get from that to moles of the base, because once I have moles of the base, I also then have volume of the base, and if I have moles and volume, I can calculate concentration. So let's write it like this. Moles of NaOH are equal to, I can take, the moles of the acid that I just calculated, 2.678 times 10 to the negative 3 moles of KHP, and I can use the mole ratio here. So I'm going to put moles of KHP on the bottom, moles of NaOH on the top, and because there's no coefficients here in the equation, it's a 1-to-1 ratio. And it quite often works out this way in a 1-to-1 ratio, but occasionally you will end up having to do a calculation in this step. So as time goes on, sometimes we don't show this full step, like we shorten this up whenever we realize it's a 1-to-1 ratio. So I'm just going to say then 2.678 times 10 to the negative 3 moles of the NaOH. Okay, now I can just I now have moles and I have volume, so I can answer the question, which is to calculate the concentration. I'm just going to remind myself that it's the concentration of NaOH by doing C equals N over V. Moles is 2.678 times 10 to the negative 3. And volume, I just want that in liters, so I can get my concentration in moles per liter, is 0.02348 liters. And that equals 0.1141 moles per liter. Okay, so you have done these calculations before. It just goes back to closer to the beginning of the semester. Another way to calculate this, it's very much the same. Like it's really exactly the same as what we did here, but it's just rolling it all into one big equation. So if you prefer, you could write it out like this. It's up to you though. So if we're calculating the concentration of NaOH, I could start by taking my grams, 0.5468 of the KHP, converting that to moles is what I did first. And then I just kind of work my way through from moles of KHP to moles of NaOH. And that was 1-to-1. And finally, I can do moles per liter. So if I just put liters on the bottom, and then you can just put a 1 on the top, right? Because I want to get an answer in moles per liter. So you would work your way through and get the same answer. Okay, so just 2 different ways to do the same thing. Choose whichever way you like best. All right, so problem 2, how many grams of KHP are needed to neutralize 18.64 milliliters of a 0.1004 molar solution of barium hydroxide? Okay, so we have a different base this time. Last time it was sodium hydroxide, this time it's barium hydroxide. So we need to write out the neutralization equation again because it's different. So we're adding that to KHC8H4O4. Okay, and barium is gonna hook up with everything except the hydrogen here. So BAKC8H4O4. Okay, and then plus the hydrogen is going to hook up with the hydroxide to give us water. Oh yeah, and barium, this is a negative ion. Oops. And it's like a -1 charge, and barium's a +2. So you'd need a 2 there. Okay, so what we do then is we need to balance it. So I'm going to need to put a 2 here. And then I've also got this 2 for hydroxide, and I just made 2 hydrogens there. So I'm going to put a 2 there to balance everything out. All right, so there's my balanced equation. Now I'm going to start by finding moles of the known. So what I know is I know the concentration and the volume of barium hydroxide. So this time, to find moles of what I know, I can just rearrange C equals N over V into N equals CV. So I'm going to put in the concentration of barium hydroxide, moles per liter or molar, times the volume in liters. And when I multiply those, I get 1.8715 times 10 to the -3 moles. Now I go from moles of the known to moles of the unknown. So the unknown is the KHP. It's always going to be, the unknown is the one like you're being asked to solve for. How many grams of KHP? So that's your unknown. This is your known. So I'm going to take the 1.8715 times 10 to the -3 moles of BaOH2, and I'm going to use the mole ratio. Now, in this step, we actually don't have a 1-to-1 ratio. So on the bottom, I'm going to put moles of BaOH2, and on the top, I'm going to put moles of the KHP. Okay, I've got 2 moles of KHP and just 1 mole of BaOH2. So I'm multiplying by 2 to get 3.7429 times 10 to the -3 moles of KHP. Okay, now my end goal here is to get how many grams of KHP. So if I just write mass of KHP, I would take my number of moles and I'd use the molar mass to get to grams. Okay, so moles, in 1 mole, how many grams? Well, we actually figured out the molar mass of KHP in the last question. It was 204.2. So that works out to 0.764 grams. Or we'd probably just round to 0.76 if you were to actually measure it on a scale. Alrighty, so there's another type of question you might come across. Okay, so those are some titration problems you could come across. Let's move on to something called pKa. So we already know about Ka and Kb and pH and pOH. So what is this pKa? So I'll go through this little part of the notes and the formula, and then I'll kind of simplify, why we would even bother figuring out this new value. At the volume that is halfway to the volume at the equivalence point. Okay, so what this means is, so when you're halfway to that equivalence point, like to where the acid and the base have neutralized each other, so when you're halfway there, we can simplify that to 0.5 of the volume. So half of the volume needed to titrate either the acid or the base. The pH is equal to a value called pKa. Now, pKa is just a way to measure the strength of an acid. Okay, now the reason we use things like pH or pKa or pOH is they're much, much smaller and easier to understand numbers compared to, say, Ka or the hydrogen ion concentration or the hydroxide ion concentration. The values of Ka, Kb, or our ion concentrations are always in, very, very small numbers and like a little bit hard to wrap our heads around. So by converting into these pH, pKa, pOH, it just gives us a more concrete value to deal with, and we can use that value to understand how strong or weak the acid is going to be. So pKa is equal to just like any P whatever, like pH, pOH works for pKa as well, it's always going to be the negative log, and in this case, because it's pKa, it's the negative log of the Ka value, right? pH is the negative log of the hydrogen ion concentration. pOH is the negative log of the hydroxide ion concentration. So pKa is the negative log of the Ka value. So let's just write this out over here. pH equals pKa. So if I write out, well, pH is the negative log of the hydrogen ion concentration, and pKa is the negative log of the Ka value, we could say, therefore, the hydrogen ion concentration equals the Ka at 0.5 of the volume that you're titrating. So another way to write this is Ka equals, if you're looking to solve for Ka, it's the antilog of the negative pKa. Or we often just write it like this, 10 to the power of the negative pKa. So just like you would do for, if you're finding the hydrogen ion concentration from the pH, you go 10 to the negative pH. If you're finding the hydroxide ion from the pOH, you go 10 to the power of the negative pOH. Works the same way. So when we get this pKa value, what does that mean? Well, a small pKa, a low value for pKa, would indicate a high acid strength. And vice versa would just be a higher pKa would indicate a smaller acid or weaker acid strength. Okay, so that's why we bother with this number. It just gives us a smaller number to deal with versus the Ka value. So another useful equation that we'll end up coming across is, or we've done and used before, is the Kw is the hydrogen ion concentration times the hydroxide ion concentration. Also, Kw is equal to Ka times Kb for a conjugate acid-base pair. So this will come in handy as we work through some of these questions. So we can determine pKa from a titration curve as shown below. Okay, so we looked at these titration curves last time. So let's take another look, and this time we're going to pick out a few different things from here. So this says 25 milliliters of an unknown monoprotic. So monoprotic is just, mono means one. So remember we talked about polyprotic acids. They involved many, like multiple steps to break down the get rid of hydrogens. They contained more than one hydrogen. Monoprotic just means only one hydrogen ion. Okay, so we have some sort of monoprotic acid pipetted into a flask, and 20 milliliters of water was added. The acid was then titrated with 0.0985 molar solution of sodium hydroxide. Here's the graph. Here's the titration curve. Okay, so what can we pull from this? Well, here's the equivalence point. So let's just say pH at equivalence equals, I'm going to say that's 8.7. Okay, it's above 8.5. We're going to say it's about 8.7. Okay, now remember we just talked about the pKa is equal to the pH at half the volume required to titrate. Okay, so we know the equivalence point is where the titration stops. Halfway to that volume is this 0.5 V, okay, and that's when your pH equals your pKa. So if you look here, at the equivalence point, if you go down to the x-axis, you can see that the volume required to titrate is 25 milliliters. So if you're looking to find the halfway point, it's just half of 25 milliliters. So that's 12.5 milliliters. Okay, so we're going to say the volume at equivalence is 25 milliliters, and we'll just put that into liters because we will need it in liters to do our calculations. So that's the volume of added NaOH. Whoops. Okay, and then at the 0.5 volume point, the halfway point, can I fit this in here? 0.5 volume would be 12.5 milliliters or 0.0125 liters. And the pKa is equal to, so if we go up and over to the y-axis, the pKa is equal to whatever the pH value is at that halfway point. And that pH value is about 4.8. Okay, so that's some new information that we can pull from this titration curve that we weren't pulling from there before. So now let's do our calculations, and we'll pull some other information from this graph that we haven't yet. So here's our neutralization reaction. Acid plus sodium hydroxide would equal the conjugate base we don't know what it is because we don't know what the acid is. We just know it's going to have a conjugate base that matches up on this side. And the other product would be water, or you could also call it the conjugate acid, right? It would match up with the NaOH. So we're going to find the number of moles of the known substance, the known solution. So looking back, the known solution is going to be the sodium hydroxide. We know its concentration and we know the volume required to titrate, 25 milliliters. So let's go. Number of moles of sodium hydroxide is going to be the concentration times the volume. The concentration is 0.0985 moles per liter, and the volume is the 0.025 liters. And that equals 2.463 times 10 to the negative 3 moles. Now, here, because it's a monoprotic acid, we don't even need to know what this is because it only has one hydrogen. This is all going to work out in a 1-to-1 ratio. Also, because this is 1-to-1, there's going to be no balancing required. So 1-to-1 ratio, therefore, moles of the acid are also equal to the 2.463 times 10 to the negative 3 moles. So what we were asked was, what is the concentration of the unknown acid? So the concentration of the acid is equal to moles divided by volume. So 2.463 times 10 to the negative 3 moles. And the volume of the acid was told to us in the question. It was 25 milliliters, so 0.025 liters. And that equals 9.85 times 10 to the negative 2 moles per liter. Okay, so no different from some of the previous questions. But now let's add in a few more details. What's a suitable indicator for this titration? So if you go back and think to the last lesson, you always want your indicator to have a color change within this vertical portion of the graph. You want it to match up with the equivalence point so that you stop your titration at the right spot. So we want an indicator that changes between 7 and 10, a pH of 7 and 10. So you could go back and look at that list of indicators, but one that changes between 7 and 10 is phenolphthalein. It actually changes between 8.3 and 10. So it would be perfect for this titration. Assuming the acid is a weak monoprotic acid, estimate its Ka value. Okay, so when it says estimate, what we're actually doing is calculating. So Ka is equal to 10 to the power of the negative pKa. So let's just write our pKa value again. We pulled that from the graph, right? It's the pH at the halfway point is the pKa. We said that that was 4.8. So if that is 4.8, then Ka is equal to 10 to the power of the negative pKa, which is 10 to the power of negative 4.8. So Ka would equal 1.6 times 10 to the negative 5. Okay, so this is just going to demonstrate why we would deal with pKa versus Ka. So here's my Ka, 1.6 times 10 to the negative 5. That is a difficult number to make sense of because it's very small. So it doesn't really stick with us as having like a great deal of meaning. Whereas the 4.8, we have a very good conceptual understanding of what that number means. So it's easier to deal with the pKa versus the Ka because it's just a more concrete, easy to understand number. Okay, what is Kb for the conjugate base? So if you remember back to the last page of notes, I said this will come in handy. Kw is equal to Ka times Kb. So we know the Kw, the K value for water, is always 1 times 10 to the negative 14. We just found Ka, so we can find Kb just by doing this. And therefore, when you divide, Kb would equal 6.3 times 10 to the negative 10. Okay, so we're just pulling some other information from the graph and from other things that we've learned today. Okay, let's keep on trucking. These last few videos are kind of lengthy, but then after today, you won't have to watch any more. Here's a problem. A student weighed 0.225 grams of an unknown monoprotic acid and then added about 50 milliliters of water to dissolve the solid. Okay, so often this volume of water is thrown in there. You're not going to have to do anything with that. Excuse me. It's just that in order to make, when you have a mass of an acid, you have to turn it into a solution. So to make it into an aqueous solution, you have to dissolve it in water. The acid solution was then titrated with a standard just means this is the one we know the concentration of, 0.1245 mole per liter solution of sodium hydroxide. The following pH curve was obtained. Okay, so here we have it. Here you would see the halfway point up the vertical portion is the equivalence point. So the pH at the equivalence point, you would have to, now it's going to be hard to show here because I don't have a ruler, but you kind of go across, whoops, somewhere like that. It's obviously not very straight, but if you used a ruler, you would find it's at about 8.4 for a pH at equivalence point. The volume at the equivalence point, again, sorry, this is going to be a mess, is about, whoa, really crooked there. It falls like about there. Anyway, so I'm going to say volume at equivalence is 17.5 milliliters. So it's, right, falling kind of between the 17 and the 18, or 0.0175 liters. Now, to find the halfway point to the equivalence point, you would divide the volume in half. 17, so you don't need to like eyeball it. This is about halfway. You would say, okay, so half of 17.5 is 8.75. So like about here. Okay, so this is going to be our 0.5V is 8.75 milliliters, or 0.08, oh, sorry, 0.0875 liters. And you could go over from there to here, and you could say that your pKa would be about 4.6. Okay, so these are all things that we can determine from that graph. Okay, so what is the pH at equivalence point? Well, we've found that already. It's about 8.4. There's going to be give and take here because it's, you know, there's no grid lines to follow. What is pKa? Well, it is 4.6. Estimate Ka for the acid. So we're going to do that by calculating Ka equals 10 to the power of negative pKa. So 10 to the power of negative 4.6, which equals 2.5 times 10 to the negative 5. Now, the last question says, estimate the molar mass of the unknown acid. So that's a little different than ones we've had before. We don't know the acid, what it is, so we'll just say acid plus NaOH produces some sort of conjugate base and water or conjugate acid. So I know stuff about NaOH. Okay, I know its concentration is 0.1245 moles per liter. The question tells me that. And from the graph, I know that it takes 17.5 milliliters or 0.0175 liters to titrate this acid. So that would equal to 2.18 times 10 to the negative 3 moles. We can see there's a 1-to-1 ratio here. Whenever there's a monoprotic acid, there's a 1-to-1 ratio, plus this is 1-to-1 in terms of how this base forms. So moles of NaOH equal moles of acid, which equals 2.18 times 10 to the negative 3 moles. So molar mass then of the acid, well, if we know how many moles we have, and we also know how many grams of the acid, we had up to 0.225 grams. So let's go. We know molar mass is grams per mole. So grams and moles on the bottom will give me an answer of 103 grams per mole. Okay, now I'm going to just keep going. That set of notes ends, and then there's 2 more titration problems. I think 2 more. Yeah. A couple pages, or like if you skip ahead in your booklet, or I've also attached them in the post. So let's just get through these, and then there's no more examples for me to work through with you. So here is an example where we have 2 aqueous solutions of acid and base. So 53 milliliters of a 0.2 mole per liter solution of sulfuric acid is neutralized by 71 milliliters of sodium hydroxide. Calculate the concentration of the base. So write out your equation. Sulfuric acid is H2SO4, and sodium hydroxide. And then what we're going to do is we're going to, make our products. So the sodium and the sulfate get together. Sodium's a +1 and sulfate's a -2. So they're going to combine like that. And then the H and OH get together to make water. So we're going to have to balance this. I need a 2 here, and then I'm going to also need a 2 there. Okay. So we're going to calculate, first of all, the known moles. So we know the acid, and we know the concentration and the volume of the acid. So concentration is 0.2 moles per liter, and the volume is 53 milliliters, so 0.053 liters. And that will equal 0.0106 moles. And then, because we had to balance this equation, it's not a 1-to-1 ratio, so we have to actually do this step. Moles of NaOH is equal to the moles of the acid that we just found, the H2SO4. And we use the mole ratio. So moles of H2SO4, we want to get to moles of NaOH. There's 2 moles of NaOH for every 1 mole of H2SO4. So multiply by 2 to get 2.12 times 10 to the negative 2 moles. All right, finally, I'm looking for the concentration of the base. So the concentration of the NaOH is moles divided by volume. So here's my moles, and my volume is told to me in the question. It was 71 milliliters, so 0.071 liters, and that equals 0.299 moles per liter. Okay, I'm going to skip over this dimensional analysis part. You can just roll all these steps into one, like I did earlier in the lesson if you like. But we've kind of been I've been solving them all this way. So I would anticipate most of you are doing it this way. But you can always look back at the example on the first page if you want to try it all in one step. I'm just trying to wrap this video up as I see I'm at 40 minutes already, which is a bit lengthy. So, problem involving the mass of an acid. So let's just do one last problem and then you're free. So 0.215 grams of an unknown monoprotic acid is weighed and mixed with 25 milliliters of water. Again, don't worry too much about that. It's just so it dissolves. The acid solution is then titrated with a 0.105 mole per liter solution of KOH, potassium hydroxide. Here is the titration curve. So we need to pull some information from here. So we're going to have to do a bit of like eyeballing. That's about the halfway point. So the pH at equivalence would be about, if you, well, I guess I didn't quite hit that, did I? I think this is supposed to be the halfway point. So is about 8. The volume at equivalence, if you go down, that one's an easy one to read because it's right on the line, is 25 mils or 0.025 liters. So the halfway point then is half of 25, which would be 12.5. So this would be the 0.5 V is 12.5 mils or 0.0125 liters. And if you go across, wow, very messy, but the pKa then would be about 4.7. And I would definitely, there's leeway there, right? It's not easy to see exactly what that value is. I'm saying around 4.7. So the pH at the equivalence point is, well, I shouldn't put an equals because I'm just going to say around 8. The pKa, we just said, is around 4.7. Therefore, the Ka is going to be 10 to the power of the negative pKa. So 10 to the power of negative 4.7, which is 2 times 10 to the negative 5. What's the molar mass of the acid? Okay, so now I go through all my calculations. I find the number of moles of the base. So I know the concentration and the volume of the base. I know the concentration is 0.105 moles per liter. And from the graph, I found that 25 milliliters were required to titrate the acid. So when I multiply, that's 2.63 times 10 to the negative 3 moles. Now, I should have, did I write it out? No, I should have written out because it's a monoprotic acid and it's, well, it says NaOH, but then in the description it says KOH. Either way, it doesn't matter. They're both 1-to-1 here. So when you make your equation, you'd get some sort of conjugate base plus water. Point being, it's a 1-to-1 ratio we're dealing with here. So the number of moles of NaOH, or I should say KOH, if I'm being, depends whether you're looking at the graph or the question. doesn't really affect the results though, are equal to the number of moles of the acid, which is the 2.63 times 10 to the negative 3 moles. So finally, molar mass of the acid is just taking the grams that was told to us in the question divided by the moles to get an answer in grams per mole, which is 81.7 grams per mole. Okay, and finally, calculate Kb for the conjugate base. So this is where we use Kw is Ka times Kb. Kw is always this value, assuming the temperature is like room temperature. And our Ka value that we calculated earlier was this. So let's find Kb. So we'll divide by 2 times 10 to the negative 5 on both sides. Kb then equals 5 times 10 to the negative 10. And there you have it. Hooray! Okay, so we're all done. 46 minutes later. So you can work on worksheet 11, and then we will review on Friday.